Find the Fourier series for f of x equals x cos x where x belongs to range minus pi to pi. Notice that this interval is of the format minus a to a. Let us check whether the given function f of x is even or odd. We will evaluate f of minus x. We will just replace every x by minus x in order to evaluate f of minus x. We have f of minus x equals minus x multiplied to cos of minus x. Since cos of minus x equals cos x, we have f of minus x equals minus x cos x. That is, f of minus x equals negative of f of x, which ensures that the given function is odd function. Hence, we have Fourier coefficients a0 and an will be 0. We have bn equals 1 by L integral minus a to a f of x sin pi n x by L into dx. Since L equals pi here because c equals minus pi and c plus 2L equals pi, we have bn equals 1 by pi integral minus pi to pi x cos x into sin nx dx. We have x cos x is odd function and sin nx is also odd function. Product of two odd functions will always be even function. Thus, this integral is of the format integral minus a to a even function into dx. Thus, we have integral minus pi to pi x cos x sin nx dx can be rewritten as 2 times integral 0 to pi x cos x sin nx dx. Since we have trigonometric identity, 2 times cos A sin B equals sin of A plus B plus sin of A minus B, we can rewrite 2 times cos x sin nx equals sin n plus 1 into x plus sin n minus 1 into x. Thus, we arrive at this integral. Here we will integrate using integration by parts considering x as first function and this square bracket as second function. We will write the first function x as it is and we will write the integral of this complete function here. Minus derivative of x with respect to x, which is written here. Integral of this function is written here. Next time when we take derivative of first function, it becomes 0 and hence we can stop the process of integration by parts here. Notice that here we have n minus 1 appearing as denominator and hence these terms will be defined only for n not equal to 1. When we give upper and lower limits, notice that both the sign terms will disappear. This is because sin pi or sin n pi or sin 0 are all equal to 0. When you give x equals 0 here, this term will also become 0. Hence, we have only the upper limit x equals pi will give us non-zero answer. We have bn equals 1 by pi multiplied to pi into minus cos n plus 1 into pi by n plus 1 minus cos n minus 1 into pi by n minus 1. Since cos n pi equals minus 1 the whole raised to n, we have cos n plus 1 pi equals minus 1 the whole raised to n plus 1 and cos n minus 1 pi equals minus 1 the whole raised to n minus 1. When we consider minus 1 multiplied along with this term and minus 1 multiplied along with this term, we have minus 1 the whole raised to n plus 2 divided by n plus 1 plus minus 1 the whole raised to n plus 2 divided by n minus 1 obtained after we have cancelled these two pi which is common to both numerator and denominator. When we take minus 1 the whole raised to n plus 2 common from outside both terms, we have bn equals minus 1 the whole raised to n plus 2 multiplied to 1 by n plus 1 plus 1 by n minus 1. On taking LCM here inside the square bracket, we will get it as 2n divided by n square minus 1 and this term is valid whenever n not equal to 1. Now let us find out bn when n equals 1. When you give n equals 1 here, we will get b1 equals 1 by pi integral 0 to pi x multiplied to sin of 1 plus 1 into x plus sin of 1 minus 1 into x into dx. We have sin of 1 minus 1 into x becomes sin 0 which is 0 and sin of 1 plus 1 into x becomes sin 2x. Thus, this integral reduces to 1 by pi integral 0 to pi x sin 2x into dx when n equals 1. Here again we can make use of integration by parts and we have b1 equals 1 by pi x multiplied to minus cos 2x divided by 2 minus 1 multiplied to minus sin 2x divided by 4, to which we will give the upper and lower limits pi and 0. We will get b1 equals minus 1 by 2. We have sin term will disappear on application of both limits. Here when you give x equals 0, this term will also disappear. Therefore, x equals pi will only give us non-zero answer. This pi and this pi get cancelled and we have minus cos 2 pi divided by 2 which becomes minus 1 by 2. Thus, we have f of x equals minus 1 by 2 sin nx plus summation n ranges from 2 to infinity minus 1 the whole raised to n plus 2 into 2n sin nx divided by n square minus 1, which is the required Fourier series expansion. This is the coefficient b1 multiplied to sin nx for n equal to 1, and here we have bn equals minus 1 the whole raised to n plus 2 into 2n divided by n square minus 1 for n not equal to 1, which is written here for the summation n ranges from 2 to infinity multiplied along with sin nx. Recall that Fourier coefficients a0 and an equals 0, and hence we have Fourier series representation obtained in this format.